My name is Kyle Banker, and I am a software engineer at Tengen. Tengen is the company that produces the open source database MongoDB. Has anyone here not heard of MongoDB? Good. Okay, pretty much everybody knows what MongoDB is then. So I spend most of my days working on MongoDB. In particular, I work on drivers, but I also work with clients a lot, and I help them solve problems and implement solutions. In the course of doing that, Richard and I, and Richard will introduce himself in just a moment, who's a colleague of mine, came up with the idea that we needed to think about how we can do transactions in a database like MongoDB. The problem with MongoDB is that it acts as both a standalone single-node database and also as a distributed sharded database. And one of the design goals, therefore, is to have the database function or present the same interface as a single node as it presents when it's distributed or sharded. And so we want your application not to have to change when you have to go to a sharded deployment. And therefore, one of the features that we don't support is multi-object transactions. But we do support transactional-like semantics. So for instance, we can do an atomic write on a single document. So we perform a certain kind of transactionality, but not the full traditional transactions that we may be used to from a traditional relational database. And so it turns out that there's some research out there that has to do with the ways in which we can implement transactions in alternative ways. And so it was Richard and my goal to present you with some of those ideas and to present you with a case study ultimately of how that's done. So I'm going to let Richard take over and provide a few more ideas and give an intro to the talk.
So good afternoon. I'm Richard Kreuter, colleague of Kyle's at Tengen. To sort of add to what he said about why we wanted to give this talk and why we wanted to get people thinking about these ideas of how to do transactional systems without necessarily relying on database transactions, there's another facet of how MongoDB and other sort of newfangled technologies are being used, which is that they're often being used in tandem as part of a hybrid approach for data storage with other sorts of data representations. So you'll see MongoDB used as a component alongside traditional SQL systems, alongside Hadoop systems, alongside a variety of other systems to comprise the sort of back end, so to speak, behind a number of different applications. The upshot of which is that even if any one of those systems supports kind of rich transactions, which we'll get into in a moment, the overall software architecture that relies on a hybrid approach just of necessity cannot trivially take advantage of a single database's transactional functionality. So just to tell you what we're going to tell you, this talk is structured into a small number of sections. A brief preamble to motivate some examples of thinking about what exactly you get from a strongly transactional kind of traditional ACID kind of database. Very short review of a few articles that have helped us, Kyle and me, think about how to do software architecture in the face of transactionless data stores for the purpose mostly of supporting MongoDB users. A discussion of what functionality you actually need from underlying data stores and what sort of techniques an application architecture may adopt in order to get the job done in the presence of hybrid approaches or transactionless systems. A rather involved study of one kind of application, and then sort of an open-ended discussion of trade-offs and sort of future things and so forth. So to start with, like a lot of people here, I took an undergraduate databases course once upon a time. And in the undergraduate databases course, there was this, week one, day one, the fundamental motivating example of why you need transactions in a database type system is to transfer funds from one bank account to another, And in fact, I did this morning, and I'll get back to that in a second. So you have two bank accounts, A and B, and you want to transfer funds from one to another. And in the thought experiment, they say, of course you need a transaction, because if you're debiting one account by N dollars and you're crediting another account by N dollars, and you don't do this within the confines of a transaction, either way of ordering the debit and the credit is going to either decrement the total sum of money in the universe or increment the total sum of money in the universe, at least temporarily. And so we'll violate the conservation of money, and that's bad. In fact, I did a transfer this morning between two accounts in one bank, and it doesn't actually work like the textbook suggests it ought to work, possibly for purely historical business reasons, but either way, it's just the reality of things. What they actually do is they debit one account, at my bank anyway, maybe your bank is better. They debited one account and created some sort of repository for the transferred money that didn't belong to me. The money that I transferred for the next 36 hours is effectively in limbo, as far as I'm concerned. And one day, maybe tomorrow, if I'm lucky, the credit will occur to the other account. So the conservation of money has been preserved from the bank's point of view, but not from my point of view. So real systems tend not to actually do what Chapter 1 of the Undergraduate Relational Databases textbook suggests they might or should do. More generally, think about the system where you're actually transferring money between two different banks or just any kind of multi-database system. The bank case is a pretty good concrete example because if you're issuing a transfer from one bank to another, I mean, there are well-understood algorithms for multi-database commit, but they all require sort of one driving program or one driving process to be in control of the exchange between the two databases. And if you're doing something that crosses domains like two different banks, neither one is actually going to trust the other to be in control of its own bank account. So the actual systems in the world are considerably more complex and can't happen just between one begin and commit. They happen by much more complex representations of state that are visible during the sort of long-running real-world process. So this was just to sort of get your brains warmed up, if they haven't already been today. So for our terminology, we want to distinguish between two different things that we're calling somewhat glibly transactions. A database transaction is the thing that we're all sort of happy to have when we're using a traditional SQL ACID type system. It's atomic, it's durable, it's isolated for some definition of isolated. It's a set of transformation state, a set of transformations of state in some system. And you guys probably know what this means. I should point out that we're explicitly not talking here about consistency within a single database because transactions in principle are sort of logically orthogonal to the consistency constraints that are enforced within a single database. A single database constraint that requires that the sum of the sum column add up to some value. In principle, that's a feature that's implemented that prevents you from committing a transaction, but you can imagine a system that didn't have any such constraints at all that nevertheless gave you atomicity of state transformation, atomicity, durability, and isolation of state transformations. Now, we want to contrast this concept of a single database transaction, which is the kind of thing that, for instance, systems like MongoDB doesn't have at a large scale, from the more general idea of a process or a procedure, what we'll call a transactional procedure, which would be a program or set of programs or some kind of software system that does some kind of transformation of state in a manner that preserves invariance at the beginning or at the end of the process, but may, for the duration of the running of the procedure, expose intermediate states that are not, that don't satisfy whatever kinds of invariance you're talking about. So this is where transactional procedures are where, for the purposes of our thinking about things, consistency becomes more of a factor. So one kind of transaction that you might want to perform would be to say, I have an example later on that I want to save for later. I don't know, you might want to purchase a couple of objects and only buy them both or neither. You can imagine a system that didn't have a database that didn't have hard transactions in the database that could support that sort of thing by means of an application that verified that either it performed both the purchases, or neither. Actually, that is my other example. So we want to talk about software systems that are transactional in their presentation to the clients of the software, but not necessarily in their operations on possibly a number of different data stores with which they interact. And at this point, I'm going to turn it back over to Kyle.
All right, so we want to talk about a few of the sort of trade-offs of these two, I guess, techniques, one of which being database transactions and the other transactional procedures, as Richard talked about. Obviously, transactions are really handy. It's nice to have that tool. It makes your life as a programmer a lot easier, and you all know what we're talking about when we say that. But, by the same token, if we rely too much on a database transactions, we might have a very tight coupling between our application and our data store. We may not be able to design our application as modularly as we like, and we may not be able to represent processes that span time and systems and space as efficiently. So, by the same token then, or on the other side of the token, there's this transactional procedure which allows us to decompose our problem into a set of atomic work units, basically. So what we're able to do is we're able to model a real-world process, recover gracefully from failures, and basically permit the distribution of work across systems. We're thinking a lot about how work distributes over time and over space and over systems, and if we can think of it in terms of transactional procedures, then we can solve those problems very well. Of course, the problem with transactional procedures is that the database does less work for us. We have to do a lot more work on the application end, and it requires very careful testing and coding. So I'm sure that, yeah.
So just to interject, the kind of thing that we're talking about when we say a transactional procedure would be something that, from a certain perspective, might actually be thought of as not even a first-class entity in a software architecture. So, for instance, suppose you're selling a physical object to someone. You're implementing, some sort of company that's selling something. A customer can browse and select objects and purchase them, and then you have to bill them and you have to ship them something, and perhaps they could even cancel the order during the duration because, again, we're talking about something that models and it fits into a real-world process like delivering an object to someone in the world that takes time. For the purpose of maybe selling, a piece of electronics, in principle anyway, there's a 90-day window during which they could return the object, and there would be restocking fees. And for the purpose of your business logic, if you wanted to think about that as a kind of first-class transaction, that would be obviously ludicrous to try to perform within a single relational database transaction because its duration is going to be at least 90 days. And that was supposed to be a laugh line, but oh well. So systems, nevertheless, have to implement these kinds of integrity constraints that either the person got their piece of electronics or they didn't, and they either returned it within their warranty or their return time or they didn't, and they were issued the restocking fee or they weren't, and so forth. And, of course, there are other real-world complexities like inventory. The inventory that's represented in your database could not be represented could not correspond to the reality in your warehouse. And so there are all sorts of ways in which the reality of what your system has to do outside of just the software. If you actually remember that most software is backing up something that is not purely bits. Once you start thinking about things in this way, there are invariants that this system has to maintain, but those invariants are not something that you would ever attempt to try to fit into a single database transaction. But they nevertheless have to be preserved, or they ought to be preserved by your overall software system. And so thinking about ways of making your software system function this way for such a long-lived as 90 days long transaction, that scales up in time. It also scales well down to the individual interactions that you might have with a system that doesn't implement transactions at all, which is sort of a kind of nice property of these of this way of thinking about what it is that your software has to do. Thanks.
Right, I think that's a really good example. I think it's hard to understand what we're actually talking about if you don't think about concrete examples in the real world. And so to go along that route, there's this paper, and it's a very compelling paper, and it's a very easy read, and I highly recommend that you all look at it. And it's called Your Coffee Shop Doesn't Use Two-Phase Commit. Has anybody in here read that particular paper? A few people, okay. So it's a really great metaphor for the idea of a transactional procedure and why that might be important and even efficient in a system that you're building. And if you think about going to Starbucks, for instance, because this is the idea that the author Gregor Hoppe presents, he says if you go to Starbucks, your order of mocha cappuccino does not happen within the space of a transaction. In other words, you don't go up to the register, the guy sitting at the cash register, and pay him your money and tell him what you want, and then wait for the particular order to finish, right? He sends that order off on a kind of asynchronous queue, and then it goes off to the barista, and he makes your coffee, and then you pay. But, and that's the way we do it, and we do it in this asynchronous, decoupled sort of way, and not in a transaction, because we want the system to be performant, right? So, but what does the proprietor of Starbucks want? The proprietor of Starbucks wants to maintain certain invariance, right? He wants to make sure that he gets paid for the coffee that's made. He wants to make sure that you are satisfied as a customer, right? So there are all these interesting examples, and there are these invariants, right? And there are, therefore, a lot of different cases that have to be dealt with along the way, right? We're not doing the whole thing within a transaction, so what are the different kinds of cases that we have to account for? Well, one of the cases is if I tell the guy that I want a mocha frappuccino, and then the guy goes off and sends it to the barista, and then it turns out that I forgot my wallet. Well, then there has to be some type of compensation mechanism. And the person at the register has to say, well, I'm sorry, we can't give you your coffee, and they might have to throw away the coffee. Right? Or there's the other case where somebody actually makes the wrong coffee, or you can imagine all kinds of situations where this sort of beautiful idea of me buying a mocha frappuccino and everything working out perfectly doesn't actually work out perfectly. And so there are these mechanisms built into the process that allow the process to come together in an invariant way in the end, right? Everyone being happy and everyone getting their money, right? Without also impeding the performance of the system. So when you're thinking about decoupled systems, there's an argument to be made that you can possibly build a more performant system, and even a more sort of rigorous system, and a system that is more able to cope with failure, if you use more of a transactional procedure that has mechanisms that allow it to compensate for situations where things go wrong. And the thing is, the great thing about the metaphor is that it demonstrates that these real-world processes are decoupled. They happen over space and time, right? The making of your coffee happens over space and time. But that you can design a system such that it will preserve the invariance that you need to preserve over the course of time, and you can get other advantages from that. So anyway, I highly recommend that paper because it gets to that idea that a transactional procedure might be a really viable way to design a software system.
So in bizarre fashion, we happen to have listed our articles in reverse chronological order. The two articles that I'm about to describe to you are somewhat less readable, but nevertheless interesting. So Hector Garcia Molina and Kenneth Salem published a paper in 1987, actually, called Sagas. Has anyone ever heard of the Sagas pattern? One person quietly said yeah, but nobody raised their hands. So I'm going to take that as a very small endorsement. So there's or a small recognition. So there's a book whose name I don't remember, but it's something like SOA Patterns that talks about patterns for service-oriented architectures, and one of the patterns is the Sagas pattern, which was first characterized not as a pattern, but actually as what was supposed to be functionality in a database itself. Nevertheless, it was first characterized by Garcia Molina and Salem. And the idea is that certain sorts of long-lived transactions, whether they exist, whether they're interacting with the data that lives in just one database management system, or whether they have to span multiple database systems, are best understood as a sequence of smaller transactions. And there are well-understood ways of performing nestable transactions, but nestable transactions are not necessarily a great fit for very long-lived what we're calling transactional procedures, so long-lived exchanges between interoperating parties. And so simple examples would be things like if you're selling something, perhaps the entity that's doing the selling isn't actually the entity that holds the inventory. So maybe I'm selling something on behalf of someone else. And so when my customer purchases something from me, that corresponds inside of me into a purchase from a third-party supplier, possibly several third-party suppliers if I'm building someone a custom object out of parts. I also have to generate billing instructions. I have to, maybe I have to do several other kinds of internal transactions within my operations. Now, each of those transactions can succeed or fail independently, but the overall exchange with my customer is satisfied only under certain circumstances. If my customer pays me and my customer receives whatever I'm supposed to be delivering to them. Garcia Molina and Salem characterize a process for doing this, which is also now described as a kind of pattern of software architecture, whereby each of these transactions is implemented in the ordinary sort of way, by having some kind of system that supports either transactions or even just very simple kinds of read or write operations, some kind of API for state change. But the overall system is not actually implemented within the scope of a single transaction that's like a parent transaction to all of these. Instead, you have what's called a saga, where state that represents the current state of a program, dependent on how many subtransactions it has performed, is propagated into that program's, let's say, persistent storage in such a way that the program could perhaps be paused and restarted for a very long-lived transaction, or various sorts of possibilities are available, and I'll get into a little bit more detail in the next slide. But the basic idea is that the separate subtransactions are fairly loosely coupled, or actually completely independent of each other, in fact, and the overall saga of sequential transactions can maintain about itself enough information to be able to either roll back the saga, not necessarily by rolling back the individual transactions, which may have been committed already, but by doing something to sort of undo those transactions. Or by possibly even rolling forward the saga. That is, if some of the transactions have succeeded and one of them fails, possibly retrying. So let me actually go into a little bit more detail about that. So the oldest paper that we recommend for the purpose of thinking about this was actually a very early paper by Jim Gray from 1981, which I think may be the first introduction of the idea of a compensatory transaction. So in a long-lived system that has to perform many transactions, acquire some inventory from my supplier and issue a bill to my customer as two separate things going on in separate databases. Sometimes you might have a sequence of these transactions to perform, and the overall software system, what we're calling the transactional procedure, might perform a number of them and then have to do something because the next transaction failed. So as a specific example, suppose you wanted to book a multi-leg flight. What's a good hub nearby? What's a good hub nearby here? So a flight from Los Angeles to Chicago and then Chicago to St. Louis. If you wanted to book that flight, you can only book that flight if you can get both of those legs. In principle, you could book, you can imagine a more complicated story, but you could book one of those legs and not the other. The overall transactional procedure that's trying to book the flight for me, upon the failure of one of these bookings, one of the legs, has basically two options. If it's booked one leg and can't book the second, then it could either fail the whole transaction, and I'll talk about that in a second, or it could pause and retry the second leg, possibly with a different kind of strategy, or maybe even with different instructions for how much it's willing to pay. You can imagine sort of smart agents doing that sort of thing. Now, the compensatory transaction, in this terminology, for the failure of the second leg booking. So let's say that the program has booked me the leg from Los Angeles to Chicago, but fails to book me the leg from Chicago to St. Louis. The compensatory transaction, in this case, for effectively undoing or something, the first transaction is not to be able to roll back, because that first transaction has already been committed. A purchase order has already been generated for the first flight. The compensatory transaction in this case is actually to do something semantically analogous, but outside of the scope of the database transaction, which is to issue a cancellation order. So basically to do another operation against the original vendor. And again, in this case, these could be separate vendors selling you the tickets for the different legs. The compensatory transaction in this case is to go out and say, oh, I want to cancel this reservation. And that effectively rolls back the saga. Now, it's a different transaction. It's a new transaction against the vendor of the first ticket. But it's, from the point of view of the saga, so to speak, in the terminology of the later paper, or from the terminology of our discussion, for the purpose of the transactional procedure, it's the rollback of the application-level transaction. And you can think of more convoluted examples. In a payroll system, if someone is issued the wrong paycheck, with the wrong amount of money, if it's too little, the compensatory transaction is probably not to cancel their paycheck, but to issue them another paycheck that makes up for the shortfall. And the converse, if they're issued a paycheck for too much money, the compensatory transaction is to take it out of their next paycheck. So compensatory transactions is a sort of, I think it's a useful toolkit for your thinking about software architecture, because it's not just rolling back a transaction in a database. It's not the same as restoring the state to what it was before you messed with the state. It's doing something semantically to sort of put your invariants right again in a way that may not even be enforceable within the context of a single database. Right, and of course the other idea within the concept of a multi-transaction saga, so to speak, is that you can also imagine rolling forward, provided that all of the state that's necessary for the transactional procedure to pick up from a let's say a system crash, provided that it has whatever local variables in the program, so long as it's persisted those, you can imagine such a long-lived transaction being able to pick up after a failure and proceed with its subsequent transactions. So let's say I want to book, a 5-leg flight. I book 3 of them, and power goes out. You could imagine it's pretty straightforward how you might architect a system so that before it does any of the bookings, for instance, it records that it wants to make 5 bookings into some persistent state, some persistent store, and then it performs some number of bookings, and then the power goes out. Well, it can pick up from where it left off and figure out, oh, I've already done 3 of these 5, so I need to do 2 more. So you can have sort of roll forward attempts to to perform a transactional procedure via the sort of saga pattern as well. So at this point I will hand over to Kyle.
So the question is, what do you need in order to implement a transactional procedure? And we want to kind of describe here the raw technical requirements and also the basic techniques that you'd need to have in order to implement transactional procedures in a system of your own. So first, to talk about the technical requirements, you can implement transactional procedures with any data store having the following properties. First, an atomic read, modify, write semantic across a single unit of data. So as long as you can read, modify, and write a single unit of data, you're almost there. You need durable writes so that you can actually record the write durably, right? We need to make sure that the state of the system is preserved so that we can come back and compensate, for instance, if we have to compensate. We need consistent reads. I think that's a pretty obvious requirement as well. We need to be able to read every write that we make. And isolation, well, the application provides a kind of soft isolation. And what we mean by that is that we record state such that the application is able to read the state of the database or the data store in general and respond to it appropriately. So we don't need to isolate the entire transactional activity or the procedural transaction from the application as a whole, but when we read the state of individual objects, we should be able to say that, okay, these are in the process of being, these are in the middle of a procedural transaction, so we can safely ignore these things right now. So, those are the basic requirements. A lot of data stores have these requirements. From obviously, a sophisticated relational database system has these requirements, has these features, MongoDB has these features. Google's Bigtable has these features. And there's actually an interesting paper about implementing transactions on top of Bigtable using a system called Percolator. And there's a famous Google paper about this. And basically, they talk about using these sort of primitives, these read, modify, write semantics, consistent reads, durability, et cetera, to build transactions into their search indexing. So this is definitely a technique that's used out in the wild in general. So those are the raw technical requirements. There are also some techniques that you want to use. And you should be able to conclude or deduce what these are, but I'll let Richard go over them really quickly here now.
So the way to think about the architecture of a system that is designed in the way that we're sort of attempting to motivate is the idea that the software itself, because it can't rely on a single kind of relational database style transaction that it can just say roll back and hope for the best, or rely on the best actually, has to be architected in such a way that after performing any write operation that is visible to any kind of concurrent instance of the application or any other concurrent application, that is to say, after doing a commit of a sort of sub-transaction, it needs to know how to do something that is compensatory from the application's semantic point of view. So in the case that I've described before, if you have to purchase multiple things, like legs of a flight, legs of a travel itinerary, if it's an all-or-nothing kind of problem, the compensatory action is to cancel your orders. More complicated examples would be things, we're actually going to have a more complicated example in a moment. Other sorts of examples might be things like those that I've mentioned, issuing a correction check for someone who was underpaid, or that sort of operation. So you need to think in the software about compensatory mechanisms for, given that the software made it to this checkpoint, so to speak, what would I need to do to get back to the original invariance that the system is supposed to preserve in the event that some subsequent transaction fails. You'll also need some sort of messaging to communicate between systems. So in the larger sense, you want to think about your systems in such a way that they can be broken up into separate pieces. So one of the sort of motivating considerations for a system like this would be one where, yeah, it might be possible that at a very small scale you can have your inventory and your customers and your, billing information all stored physically within the same relational database. But at scale, that becomes increasingly problematic. Maybe your inventory needs to be factored out into a separate system. Maybe your customers need to be represented in a separate system. And so in order to architect your system so as not to rely on the idea that all of your data is co-located into one silo, you need to be able to communicate between interoperating parts. And this is actually not that complicated. Basically, any kind of queuing mechanism is generally going to be sufficient. And as we've been suggesting, think in terms of the procedure itself being the transaction, the application itself being the semantic transaction instead of a single RDBMS type transaction.
So how are you doing with the idea of transactional procedures? It's a fairly straightforward concept, right? And it's probably something that hopefully you've thought of already. But to give just a brief example, we present just a simple case study of the idea of selling concert tickets and what that would involve, how that would involve using transactional procedures, compensatory mechanisms, et cetera. So what are the problems with selling tickets online? Well, obviously, no two seats are the same. Once we've guaranteed a particular seat to a buyer, we must allow that buyer to make the purchase if they can. Obviously, the user might not complete the purchase, and the ticket must still be available at checkout if the user actually makes it to that point in time. So some of the techniques that we might want to use, one is that we model data after the real world. So we have a physical record in our database for every physical object in the world. This gets back to that idea that the HOPA article presents, where we look at the physical world for clues as to how we can actually model our system, and that possibly informs an elegant design to our system. We implement a lease. Once the user has chosen a seat, she has 5 minutes to purchase it. And we use states and compensation mechanisms. The ticket has a given state or a series of states, and the seat can be made available again. It can be unavailable. It can be about to be purchased, et cetera. We go through this series of states. We think through this series of states and the different kind of contingencies we want to compensate for. So let's give a brief example of the implementation. We start off with a simple document. This is a JSON object, and it also corresponds to the idea of a MongoDB document. So we have a seat. It's seat number 111, and its current state is available.
Just as a minor note, for people who aren't familiar with MongoDB, just ignore the braces and the things that are on the left-hand sides of the colons. Think of them as column names. And this is just a record somewhere.
Right. So, yeah, a series of keys and values, essentially, right? So when we sell a ticket, what do? Well, for each ticket, we have to atomically fetch and modify the ticket and test for availability. If it's available, we set its state to in cart, and we associate it with a particular order ID. And we set a lease to 5 minutes in the future. So we look at our renewed example. This is one that's actually managed to get into a cart. It's seat 111, and its expiration is 5 minutes in the future, some timestamp. Now, if the seat is unavailable, then we compensate. If any of the seats that's requested is unavailable, then we compensate by rolling back the previous set of seats, right? So maybe 3 of the seats were available, but 2 ended up not being available. So we have to go back and compensate by making those available again. And there may be other ways to do that, which I'll suggest in just a second. But in this case, now the user has 5 minutes to pay. And when the user finally gets to the place where they can click Pay Now and charge my credit card, then what we do first is we atomically read, update each ticket, and we test that the ticket is still in cart and not expired at the time that we do this. And if it is, then we go and set the state to a pre-authorization. We renew our lease for the next several minutes, and then we attempt to authorize the credit card. And this is the place where we're coupled with some type of other system. So we can't, and we don't, we have to decide how long we're going to wait for such an authorization, but we have to take all these steps in order. And when we do so, first thing we do is we actually do set the data to pre-authorize, and then we wait for the authorization to complete. If the authorization fails, we compensate, again, by resetting the tickets that we've had back to available. But if the authorization succeeds, then we can set the ticket's state to sold. And this is the case that we get right here. So a couple notes about using a procedural transaction case. We're using a procedural transaction in lieu of a long-running transaction in a single database. Therefore, this algorithm that I've described, or this series of steps, or this elements of the saga, if you want to talk about the saga terminology that Richard was mentioning earlier, can be implemented in a lot of different systems. It can be implemented inside of a distributed database or a distributed system. It can be implemented on top of a database that has only basic transactional semantics. And of course, it can also be implemented in a traditional database. We also implement this using a lease mechanism and a series of states. Now, there's going to be the obvious question of what do we do in certain failure scenarios. The obvious failure scenario is, the application dies in the middle of the purchasing of a seat or the adding of seats to a cart, etc. Well, we need to store enough state or enough information inside each object to allow some type of reaping process to be able to go back in and set the state of the system aright. And that's something that we can actually do in this situation. Another kind of interesting variation of what we're doing right now is that we can actually, if we're selling just a fixed number of general admission tickets rather than tickets to specific seats at an event, then we can actually lazily expire those, right? We don't actually have to have anything that's transactional to go back and reset their state. We can imagine being able to query the database in such a way that we can reclaim tickets that have not been purchased or in the time that we've allowed them to. Yeah, sure.
One of the things that I'd like to highlight here is that for the people who haven't actually played with MongoDB in any sense, this example is sort of structured in a way that a MongoDB type application would be, where you think a lot about sort of which specific modifications to what records you perform. But in a larger sense, each one of these manipulations that was described in the preceding slides is essentially a single statement transaction. And the state visible to a concurrent application after every one of these modifications is what we were describing earlier as soft isolation. Concurrent applications would be, or sort of the application itself that's allowing you to reserve a seat for the purpose of a purchase would be coded in such a way as to simply not allow anyone to reserve a seat that was in one of these non-available states. Or it could be looking for records whose timestamp had expired already. So in this way, there's a kind of exposure of something that could otherwise, conceivably anyway, be isolated into a single database transaction. Although again, before I finish that sentence, I'll recurse into a whole different paragraph. People who do web development don't get to take advantage of this stuff anyway, because the interactions that happen between a specific piece of a web application and the database are so disconnected from each other, possibly running on a concurrent client that happens on a different box that can't share any state with the box that did the first marking of the seat as having gone from state available to state reserved. Might not have anything to do with the client that marks it, sends it from state reserved to state pre-approved. Pre-authorized. So we've actually been doing this for a long time. We collectively, as people who've been doing software development, have actually been doing this sort of stuff for a long time with very small transactions in a relational database context, or even not using transactions in a relational database context, and having sort of application invariants that enforce the consistency requirements for the system that we're trying to implement. Now, I'll admit the way we do it is largely ad hoc, and perhaps there should be tools to help us with this sort of stuff so that we could actually declaratively say, well, the compensatory mechanism for a seat being out of date, or sorry, for a lease expiring is that it can be thrown back into the pool of available seats or something like that. I'm not exactly sure what that would entail from a sort of, if you're a developer from a programming perspective, but I think that might be an interesting thing to try to isolate. But again, just to pop back to the sentence that I didn't finish before, the idea, again, is that there's a kind of soft isolation, that the data itself represents to the application whether or not it is safe to manipulate in its current state. But
right, so I think that's essentially what we wanted to present, and I think we've made clear some of the advantages, or I hope that we've made clear some of the advantages of thinking in this way. And I think it's probably true that a lot of us have already been thinking in this way, as Richard has pointed out. But I hope it gives us maybe a way of, or I guess a framework or a language or a vocabulary for thinking about what we're actually doing when we're implementing something like a procedural transaction and a compensatory mechanism. And I hope it's helpful to think in terms of, the idea that these kinds of mechanisms can be valuable for implementing, real-world procedures, messy real-world procedures, in fact, in a software system or in a database system that doesn't necessarily give us all the traditional tools that we might be used to. I think there's value in thinking about how the real world functions and how the real world functions in cases of failure and how we can sort of use that as a model for our own systems. And obviously there are certain types of disadvantages to these procedures as well. And I mean, we may in some cases simply just want to throw all this away and use a traditional database and rely on a traditional transaction. And that's also a possible response to this. But thinking in terms of this has helped me kind of, as I guess, open my mind to think about new ways of modeling our data, new ways of modeling processes, and hopefully gives us a legitimate way of expressing this and not just saying that this is not the traditional old school textbook way of manipulating data and therefore it's not valid. There actually is a framework here, and it's worth kind of validating that framework and applying it to problems that we're solving.
Right, and just to add to that, I will posit, without having thought through a good example other than the ones that we've already discussed, that architecting large systems along this way of thinking with things that don't actually need to be going on inside of a single atomic data manipulation being implemented as separate operations. If you construct your software system in this way, albeit at the cost of some extra complexity in the application, you'll have greater modularity and scaling properties, just because you're not going to be tying things together that don't need to be tied together. I mean, anecdotally, Kyle and I see this a lot among users of MongoDB, especially among users of MongoDB who deploy it as a hybrid with other systems. There might be data that's not under a particular user's control that they nevertheless have to manipulate via a sort of well-defined API that might be slow or unreliable or have callback semantics or something like that. And those sorts of things are other cases. Those are also cases where you simply need to architect your system in such a way as to be able to do the right thing for its users, the users of the system, in the presence of some pieces committing and some pieces not committing. So again, the idea is to try to encourage you to think about this and maybe isolating this aspect of an architecture, of software architecture, into something that you can actually take good advantage of. So we're a little early. First, I should say thank you, and then ask if you have any questions. So thank you. Yeah, question. So the question is there already an implementation of this pattern or a framework that implements this pattern? The answer is yes. Just scrolling back to the Sagas paper. So there's a subsequent paper that's actually considerably more boring, which is why we didn't include it in the literature review, that actually talks about implementing this from the point of view of a database implementer. So you could actually imagine a database like a relational database that has sort of a begin saga, end saga kind of operation. That's not as interesting to an application developer, but it can be done. There's a much later book, unfortunately I forget the name of its author, but I could dig it up for you if you'd like, that actually sort of patternizes the saga idea as a thing that you can then take advantage of. I'm not aware of any frameworks to do it, but it's a little bit hard to frameworkize because it has to do with your application's semantics and not just sort of the data in a declarative sort of sense. Right? I mean, so the grisly example that I've been avoiding bringing up, although I think it's sort of funny, is you can imagine a system, one of whose actions is to launch missiles, right? You can't roll that back. The compensatory action for that is probably like reparations, right? So, I mean, that's a kind of semantic thing about that software system. But anyway, yeah.
No, when you were explaining this pattern, I was thinking about a state machine that I can have the confirmation everything. So.
Sure, right, yeah.
I think that's one of the fundamental tools that you use. If you have like some kind of state machine, right. And particularly if you can model your data interestingly as a state machine, then that's obviously one of the basic tools that you'd use.
Right, exactly. Yeah.
Yes.
If you have, for example, reserving 10 seconds at a time across a partition T-space, what kind of tools do you just have to write in your own log and undo commit undo type scripts that could alternate across a different key space?
Yeah, I mean, like, I guess it depends on the database system that you're using and what kind of interface it provides to that key space. Well, in the case of Mongo, your application doesn't really know anything about the partitioning of the data. So when you read or write to the data, you read or write as if you're writing to a single machine, right? A single whole. So there's really no difference semantically in terms of the way your application behaves.
So I don't have to go program it over, then I can split this batch and all be committed to each of the permissions.
Well, that's not technically true either. You might, in the case of MongoDB, you'd actually have to do one at a time, right? And if you get a failure anywhere along the way, then you can go back and undo that or lazily undo that by some other process. Yeah. Yes.
So one of the things that is running up against is the concurrency issue, and I don't see that necessarily addressed here. In that, in your first stage reservation, what keeps two processes from identifying the same record as being available if you don't have transactional locking?
Well, no, you do need a basic kind of transactional locking. What I said in the technical requirements section of the talk is that you need atomic read, modify, write semantics on your data store for a single record, right? So if you can do that, then you can handle the concurrency situation.
So the question is, do we know about event sourcing? I've seen it. It actually, now that you pointed out, it is sort of analogous. It's the same. It's a similar kind of idea that each event would be one transaction. Right. So, yes, I agree. But I don't have anything particularly deep to say about it. Yeah. The question is, does this encourage more normalization than you might otherwise be inclined to implement? Is that the question? I'm not really sure. Could you be a little bit more specific?
Well, I was trying to imagine a situation where I might have, let's say, an alert for a financial application, and I want to send an email based on the price of Cisco and another one based on the price of Microsoft. And now each one of those documents, those alert documents, contain an email target address. But now I want to change that address.
Well, okay, so this is sort of an interesting example because sending an email is another kind of unrevertible operation, right? It's either once it's sent, it's done. The only thing you could possibly do from an application point of view to correct for whatever the semantic meaning of sending an email is to send a follow-up and say, ignore that. Well, so I'm curious about why you'd want to be changing if the purpose of storing something like an alert in a database is to record that you sent it. I'm curious why you'd ever want to change that history.
This is something that will happen in the future. When it reaches this price, send it to this address.
Oh, I see. Okay.
I'd like to change where that's going to go, but unfortunately, it's duplicated throughout the entire collection.
Oh, okay. I see. All right. Well, yeah. I mean, so this is actually a sort of this is a MongoDB specific, like how do you model data in MongoDB kind of question.
Possibly.
Yeah. The glib and short answer is don't do it like that. In that case, you would actually want to normalize things out into a single document representing this particular sort of event object's list of recipients that you would then, if you needed to keep it versioned, you could keep it versioned and have a different document for each version. But it's a little bit orthogonal to this specific thing. But we could talk about that a little bit offline. We were actually trying to avoid giving a too MongoDB specific talk.
No, that's fine. But once you pulled it out, then all of these techniques would work just fine on that.
Yeah.
Yeah.
Any further questions?
So I have a Mongo-specific question. How would you do an atomic read modify?
That's an easy one. Would you like to do this one, Kyle?
Sure. There's a command called find and modify.
Which is an
That's what
atomic
it does.
read, modify, or read, write, and return something.
You give a condition, you give an update to perform if the condition satisfies, and you get the document back in a single round trip. All right, well, we're happy to talk more about the topics in this talk or the topic of MongoDB afterwards, and thank you for all your attention today.